Okay, the goal that I have for us is if given pH curves, titration curves, we can pull information from that. So we're going to start with acid, adding base into that, really dissect and make sure that we understand, for example, here. Okay, so given the shape of the curve, what I predict, it's weak acid, strong acid, and what is the major species in my flask, in my beaker? Well, then as I add titrant, what is being changed? What calculation would I need to do to find the pH and so on? So I'd love to kind of, I guess, draw the anatomy, if you will, of what's going on in the two different curves. Then let's take a look at some sample multiple choice that'll give us particulate diagrams to enhance our understanding of the parts. Then we'll look at, well, what if we have base and we add acid? Are we good with that? And really yesterday, walking through all the titration parts and doing the calculation really is the foundation that we need. Let's pick apart this. Let's do some sample questions that have particulate diagrams. Good morning. And then look at, well, what if we start with base and add acid? And we'll see from there, probably a couple more sample questions. Okay, so first and foremost, the floor is open to you. What concerns can I address? Anything before? So I would have out our unit packet, and then I should name these or something. So if you want to just get all the packets out, but particularly we're going to need these today, along with the unit packet. Okay, so I pray that we got a good refresher of kind of the basics of titration, if you will. Oh, yeah. You're very, very welcome. Okay, so as far as terminology, of course, what is the goal of a titration? What is the titrant? What is the analytes? And what is equivalence point, which we can also call the stoichiometric point? pH curve, titration curve. Good on the terminology. Phenomenal. Okay, Aaron, you choose for us, sir. Are we going to look at the top curve or the bottom curve? What would you like? All right. Now, we're not given any markings, so we can just make the judgment call. I'd say strong acid, strong base. Yeah, this darker one. Sorry, I didn't quite. If anyone wants any colored things, I have a bunch of colored markers in case you would want. Okay, so we definitely say what I, made blue here, strong acid, strong base. And why, Aaron? What proof?
There's
wonderful. So remember, like we see here, whoop, an abrupt jump, and we'll talk about why we see that is anticipated for the weak acid to start, where here, we're just barely going to creep up, barely, as we add strong base. So you're absolutely correct. We don't get that initial pH jump. What else?
It starts slower.
So we anticipate, even though we're not given values, I mean, I think we could call kind of the middle here, might say 7, yeah? And so, oh gosh, this is definitely going to be, really close to 1, if you will. Absolutely. So starts with a low pH. We don't see that initial hill. Where would you label equivalence point? So we are starting with strong acid, and I'm going to just ignore the spectator as long as you're okay with that. So we start out with H plus and water and spectator. As we react this away, we still have a good amount of strong acid. Strong acid, strong acid, strong acid, strong acid, strong acid, strong acid. Ooh, it's almost gone, almost gone, almost gone. Whoop! We call the equivalence point the middle of the pH jump. We're always going to have a pH jump because you're still acidic, and then one drop, you'll be pushed to basic because you've reacted all the acid away. So we're always going to have some kind of little jump that takes us from acid to base. And so we guesstimate where the middle of that is. So if here is where my sharpest, here-ish, and we're eyeballing it. Okay, Joe, for strong acid, strong base, where do you know the equivalence point is? It's okay, we just did it yesterday. No worries. Okay, so we would anticipate we're adding hydroxide to hydrogen ion. Okay, add hydroxide, we're reacting away some of the hydrogen ion. But we don't react all of it away till kind of around here. And then beyond that, we're going to have an abundance of hydroxide ion. That's why we're so basic. So at the equivalence point, you have added enough strong base to react all of the strong acid, which of course is H3O+. And then we have the spectator maybe of chloride, maybe of iodide, maybe of nitrate. And then spectator of sodium ion, maybe potassium ion. So what will we have? Yeah. At 25 Celsius, what would be the pH of spectator ions that do not have the capability of being acid or base because of their weakness? You just have water. Yeah. So that would be the other evidence. So I would say low pH, we don't have the jump, you're low, big jump. See, we don't have as much there. And then the equivalence point will be at 7. All of those clue us in strong acid, strong base. Okay, so I would definitely say the upper curve is weak acid, strong base. Okay, what is the evidence? We start kind of, 3 or 4-ish. Now, we could have a very dilute strong acid. So that's not always, but that's okay evidence. We see this initial whoop, jump, levels out. And then our equivalence point is above 7. So we'll break it down. Is it okay, Alan, that for weak acid, strong base, we are starting primarily with HA, not H+. We, of course, know we have a little bit, but not enough to write down. So here's where I have my greatest concentration of HA. Okay, Colby, I have HA that I'm adding strong invader to. All right, what do we make?
Minus plus water.
Excellent. And can I just ask? So, Elena, is there a nickname I would give to A- in regards to its relationship with HA? Now, as I react, thank you. As I react this away, I'm making more of this. Okay, we're here when I react the hydrogen ion away, I'm just making more water. But here, I'm making more conjugate base and water. At the equivalence point, here, we just have water and then the spectators. But here, we have water, but we also have conjugate base which here, the concentration of conjugate base, oh, no, because we're adding volumes. That's all I'm going to say. And I'm just going to put in brackets because I know water, but that's what I have in greatest concentration. So that's why I'm putting in brackets to comment upon. It's not just there. That's what I have in greatest concentration. Okay, so as we go, this is greater than the conjugate base. Is that okay? Let me make sense of the color. The greater. Okay. All right. If this is the volume that gets me to the equivalence point, halfway there is my halfway to the equivalence point. For a weak acid, strong base, what is true there? Yes. Why are we allowed to do that? And that's what.
That's because the concentrations, isn't the concentrations equal, so that X.
So here we've reacted all of the weak acid away. Here we've reacted half of it away. And if we've reacted half of this away, we've made the same amount of that. So here, the HA is equal to the A minus. And then going to the right, the HA is less than the A minus. Then eventually we just have all A minus and then an abundance of hydroxide. Okay, $25,000 question of the day. Why don't we keep climbing? Why do we climb and then it flattens and then equivalence point? Why don't we just climb, or why do we get that flattening area? We are adding strong invader. And so, man, we're reacting away because we just start with weak acid. So that's going to make a big impact on the pH. Woo! But then not so much of an impact as we add hydroxide. Why? Brilliant ones. So we get this, whoop, but then it levels. We start with primarily all of this, adding strong invader. Man, if this is the only source of the hydrogen ion, yeah, we're taking a bunch of it down. Yeah, the pH is going to jump. But then it doesn't change much as we add strong invader. Brendan.
Like the weights are equal to each other.
Rates. I think you're thinking correct. You're thinking correct. But rate is speed. So we're not talking about how fast it goes at this point. Olivia? Say again. Say again. All right, that is a big money prize. That's a big money prize. That's a big money prize. Okay, Hershey bar, Mike and Ike's, M&M's. Ooh, big Laffy Chappy. Ooh, Kit Kat. M&M's and mechanical pencil. Brand new, never used. I just have to find where it opens. Oh. Please come forward to claim your prize. You can choose whatever color you like. Okay, so here, remember the dream buffer. The dream buffer has the same concentration of weak acid conjugate base. So this is where like the ideal protection of pH. But we would say this whole area where we're kind of flat, we call that the buffer region. Because it's protecting the solution from a drastic change in pH. So look at that. Look at that. That's why it flattens. Now here, no, strong acid. We're not making the required ingredients. So how about that? Okay. Could we please now go to this packet? Okay. And could I ask us to please do 1, 2, and 3? Okay, given this curve, 1, 2, and 3, please. And please notice it's strong acid, strong base, 0.1 molar HCl, titrated with 0.1 molar NaOH. You want to check in with your neighbor, talk through with your neighbor. Are we good to go? All right. So like I would just make sure that I understand like what is being conveyed per the key. And it helps me most to really identify where because I'm starting with strong acid, where I have that and so on. Okay, so correct answer, left to right, C, A, D, B. Okay, talk through. So here, I know I haven't added any NaOH yet, so that's going to be all strong acid. It's HCl, so I'm looking for where I just have this and this. And there should be equal amounts of both. So 2, 4, 6, 2, 4, 6. This is just my starting HCl. Okay, as I add hydroxide, I'm going to react this away. That's still going to be there. Yeah, so I'm going to see chloride because this is a spectator in each one. All right, I am making water. Yeah, making water. Oh, they're not showing. They're not showing water, but I'm reacting with the hydrogen ion. So if we take a look, oh, this has less. So, okay, where are these coming from? Well, to deliver the hydroxide, the sodium ions are being introduced. Here, I have less hydrogen ion than I started with. So I know that this is further than A, but not yet to my equivalence point. At my equivalence point, I don't have any hydrogen ion. I don't have any abundance of hydroxide either. I just have spectator and water. So I definitely know that this is the equivalence point. And I know what makes me basic is I have a remaining hydroxide. Oh, because there's no more hydrogen ion to react. So that is what clues me into there. This, I just have hydrogen ion and chloride. That's what clues me into there. I don't have any hydrogen ion or hydroxide. So that's what clues me into there. And then this is less hydrogen ion. So that's there. More clarification. So the salt, NaCl, those are just spectators. And this, neutral. Good? Definitely good. Could I ask us, please, to turn to page B? Okay, so what information can we gain from a pH curve? So we talked about like the anatomy. All right. So strong acid, HNO3 titrated with NaOH. Okay, what are we told? 50 mils of that, 0.1 molar of that. We monitored pH and we graphed it. Concentration of HNO3. Robert, I would definitely anticipate when we're asked for concentration, it's asking for molarity. What are the units for molarity, please? Yeah. Okay. That's my volume. And it's asking, you know, used in the experiment, what was it when it started in the flask? Yeah. So, well, I have 50 milliliters of it. Now, you never have to show me conversion of metric units. So I need moles. Easy, easy. Yeah. When are we allowed to use that? Do you remember? You don't have to remember this, but that constant is given a nickname. Like Avogadro's number, 6.022 to the 10 to the 23rd. So 22.414 liter per mole.
Oh,
can only be used for STP, and it's gases. So we have liters of gas in every 1 mole of gas, but we have to be at STP conditions. And we're not told conditions, we assume we're at room conditions. Thank you for reminding us of that, though. No gases here. We wouldn't have been given this unless we would use it. Okay, Aaron is a powerhouse thinker. Some of us are just checking the box that we're here. Aaron, take it away, sir.
The equivalence point is at 75 milliliters.
And look, they even put a big old dot there. Keep going.
You know that the HNO3 is higher here.
Wonderful. Wonderful, sir. So, equivalence point, stoichiometric point. Really, why do we call it that? Here, we have added enough hydroxide to react all of the acid. When we're talking about reactant amounts, if you don't mind, I'm going to be in moles. So we know 75 milliliters of 0.1 molar got us to the equivalence point. So how many moles is that? Well, if you want, we could just be in liters. Yeah, so 0.00750 moles. Well, if that's how many moles of hydroxide, we know it's a 1-to-1 mole ratio. That's how many moles then of the HNO3. So the equivalence point, if we know the concentration of the titrant and the volume of titrant that we added, think about our lab work that we do. Don't you know the concentration that you put in the burette? Don't you very carefully note first volume, the last volume, to find moles that you've added? All right. And it will be 0.15. And so Aaron reasoned, which was fantastic, fantastic. And so you said 1.5 or 1.5 times point, there you go. Yeah, you're totally fine with your reasoning. That was excellent. Okay. So could we turn now to D, page D. All right, now when we look at this, we should just know, oh, weak acid, strong base. Because higher pH to start, get that little jump, and equivalence point above 7. And don't you know? Yep. Okay, so a little more of particulate diagrams. Can you please go ahead and match from 8? So E, C, A, left to right on the top, F, B, D. Questions at all? Do we understand why the equivalence point is above 7 for weak acid, strong base? What is the dominant or the major species at E?
Water.
But then wouldn't we have a pH of 7 at 25 Celsius?
And the conjugate base.
Excellent. Excellent. Yep. And it's doing its thing and being a base. So it's making enough hydroxide, push us above 7. Absolutely. Very good. Very good. Okie dokie. Can you, in your note packet? Okay. Please turn to page 14. Any questions as we're finding our way there? All right. Weak base with strong acid. Weak base with strong acid. Okay, we have 100 mils of 0.05 molar ammonia. You don't have to draw any kind of image, but I sure do like, just to give the brain some help. All right, and I've neglected to let you know the KB of NH3, 1.8 times 10 to the negative 5th. Sorry about that. And we are titrating it with 0.10 molar HCl. Okie dokie. First thing we're asked, pH halfway point. All right, we're starting with weak base. I would anticipate 10-ish. We're adding strong acid. So we've seen what, let me just pull this back again. We've seen what, beginning with weak acid and adding strong base. We get whoop and so on. So does it go up? Adding strong acid, strong acid, strong acid. And at the beginning, we just have NH3. So it's going to be a big drop. We're going to level out because the NH3 is going to react with a strong invader to make its conjugate acid. Oh, sugar. We're going to end up with strong acid. So that, yeah, it's going to be low. So we start with NH3. We're adding strong invader of acid when we're at the equivalence point. What will we have? Water. Water starts there, making more. But what is responsible for the pH? The conjugate acid. Oh, yeah. So the only time at the equivalence point we're at a pH of 7 is if we're at 25 Celsius, strong acid, strong base, strong acid, because we just have water and spectator ions. They're too weak to be acid or base. All right. Halfway there. What would it be?
That's PO. That would be PO.
Yes. Yes. So like what? So we could say halfway to the equivalence point for a weak base strong acid titration, what can we take to the bank?
You can.
Definitely. I'm so sorry.
Oh, are those?
No. You said half-life.
Yeah. Oh, the half-life.
Yes. Yeah. Halfway to the equivalence point. Okay. Very good. So halfway to the equivalence point. Yeah. So half-life would be the time it would take. Okay. We would say the POH is equal to the PKB because the base is our dominant species. Alan, please remind us, master of math. What does that lowercase p mean?
Negative. You
got it. So take the negative log of 1.8 times 10 to the minus 5th. But that is our POH. .74. Remember, logarithm, we increase sig figs by 1. And then 14 minus POH is our pH. 9.26. Okie dokie. Last problem. Just a second ago, I thought, I need to apologize because my students just look so sad. I think it's the other way around. I'm pretty sure. I think I might deserve the apology. Looking, some of our faces look alive. All right. So, pH at the equivalence point. We will only have conjugate acid. And that conjugate acid is doing its thing. Connor, I won't insult you by asking you to give us the equation, but could you please remind us what K will describe this behavior? You got it. Are we given Ka? Ah, excellent. And so we'll have to take Kw divided by Kb to get our Ka. And we are just taking it afresh. We are just saying, okay, well, we have just made a whole lot of it. And so it's going to have what it wants to do with water. How do we find its concentration? Here.
How that it would be. What happened? 0.005 moles because they have 100 moles of 0.5 moles of NH3, so maximum NH4 plus would be at 0.005.
Just pause a second. So, given the volume and the concentration, if we convert this to liter, 0.1, and 0.1 times 0.05, 0.005. Do you want to be in millimoles? Go for it. So that's how many moles are in this original solution. Well, if I'm at the equivalence point, I've reacted all of that away, and I've made that same amount of moles of NH4 plus. So my concentration of NH4 plus initial will be 0.0050 moles. Okay, and it was 100 milliliters of the original ammonia that I added HCl to. Pick up from here, sir. How do I find out what my total volume is?
So you know that you have the same number of moles of HCl and
Yep. You're right. And so if I would do this, it ends up being, 0.05 liters or 50 milliliters. You got it. You got it. I do the calculation. You're so good that you can see like, oh, well, to do that, because of the difference in concentration, to get to the equivalence point, I do half or 2 times or whatever. Very good. Very good. All right. So let's just finish this out. All right, minus x plus x plus x. And then we're going to solve for our x. Okay, and it'll be 5.6 times 10 to the minus 10 equals x squared over 0.033 molar minus x. 5% will definitely stand. The x is my hydronium. (4.2 times 10 to the negative 6. And then pH. (5.38), which we would definitely anticipate an acidic pH at equivalence point. I'm just writing it. For weak base strong acid. All right. You know what I should have reminded you of every moment? Oh, I better stop.